Okay, so we're done with straight wire. We're going to move on to solenoid. But before we move on to solenoid, we're going to look at just one piece of a solenoid, like one section of it, and basically we're going to look at a flat coil first, okay, just an individual flat coil. So if we look at a flat coil here, this coil is made from a wire, but the wire, instead of being straight, is a coil, a loop, okay? It's a loop, a single loop, and then it comes back. So current flows through in this direction. Where would the magnetic field pattern around this coil be? Right, you can still, a moving charge still produces a magnetic field around it. A current carrying conductor, a current still produces a magnetic field around it, and it still follows the same rules with the right hand grip rule. And so if you look at this picture, which does it better than I can do through this tiny little video here, you can see that the right hand grip rule, as long as your thumb is pointing along the direction of the current, then you see that, hey, it curls inside the coil like this. Around the coil, but it curls inside and then out, right? This one does the same thing, inside and out, and it goes all around inside and out, right? So if you can imagine, what would the field look like? It will look just like this, okay? So this is the coil. When current is going through it, it produces magnetic field around it. Imagine if this 3D, it's all around it, so it's all kind of like curving in and coming out of it. Okay, yeah. So this is what you get from the right hand grip rule. If let's say you want to look at it from another perspective, using the pictorial representations, right? So this is also a coil, a loop, right? Current is coming out of this wire, going down into this side. Let's look at that side first. If you look at these two as separate wires, separately, what do you get? So this one is going down into the paper. So if you're looking from top down, you represent it as an X, and because its X is going in, right hand grip rule again, the magnetic field coils around in the clockwise direction. Right? If you look simply at wire 2, it's coming out of the paper. It will be anti-clockwise direction. But these are not two magnetic fields in isolation. They're not very far apart from each other. In fact, they will overlap with one another, right? So the effects of the magnetic field will overlap with one another. And so if they will overlap with one another, this is what you get. Okay, can you see that again? So they're not apart from one another such they don't interfere. They actually, in fact, the magnetic field doesn't end here, right? It kind of goes on just as it's weaker, right? So if you move them closer together like this, they actually overlap. And what do you see here? You see that at this portion, the magnetic fields, they kind of complement each other. They kind of add to each other in the same direction. They're all pointing to the left in the middle. Okay, so can you see how in the middle they're all pointing to the left? So they'll add to each other. You see how they're really close together? They'll add to each other and be much stronger in the middle. And what do you see at the sides? Hey, at the sides you see that it's much weaker compared to the outside. Of course, the magnetic field lines you don't draw them like this, because rule number 1 of magnetic field lines, they never cross, right? But in this case, you can kind of get an idea of what it will start to look like, because down here it'll be very, very strong inside of it. Okay, so what does it actually look like? Let's look at handout 2, question 2. Okay, handout 2, question 2. Draw the magnetic field pattern surrounding a flat coil and determine the magnetic pole. So this is a flat coil, or you can just think of it as two wires, but it's a flat coil. So this is the wire coming out here, and then it's going in from this side. It's a coil. Okay, how will you draw this? So you know that for this one, this is coming out of the page. So right hand grip rule tells you that it'll be in this direction, right? And then this one is going into the page. You use your right hand grip rule, then it's also going in this direction. So just by this is not, don't draw this first. This is just to show you what it looks like. So this, we know the inside is going to be really strong, outside is going to be weak, and inside is going to be pointing in this direction, right? Okay, so let's redraw this to how it's supposed to look like. So inside, how I'm going to do this is I'm going to start with this one being very close and getting a bit further away, because I want to show that it's weaker on the outside, right? So this is the first one. Then I'm going to draw another one quite close as well that gets weaker further away. Then I'm going to draw a curve down like this, Okay, and then one more. Okay, so in reality, of course, this is actually forming a loop around here and then coming back, but because of lack of space, I'm just going to draw it like that. Okay, so and that's how you're supposed to draw it as well. So same thing on this side, draw one like this. Okay, this is quite tricky, so do try it on your own to get the idea. Okay, then one that comes in like this, and one more. Okay, remember your fill lines can never cross each other. Okay, so it will look something like this. It says determine the magnetic poles. So if this is like an electromagnet, where are the poles? Okay, this is a bit tricky because usually we say the field lines always point from the north to the south. But remember, if this is a magnet, we're looking at where the field lines are coming out from, and the field lines always come out from the north. So if you imagine this to be a magnet, right? If you imagine this to be a magnet, actually, if this is a magnet, it looks like this. Where's the north pole of the magnet? Can you see that the field lines are coming out of this side? So actually, this is the north pole and this is the south pole. So inside the magnet, it actually you can kind of imagine it to go from south to north, but really, we're looking at which direction it points, and so it always points, it's coming out of the magnet. It always comes out of the north pole of the magnet. Okay, if you're looking at this as mini magnets, remember the domains, all the domains inside the magnet, they're pointing north, pointing north, pointing north, pointing north. So this side must be the north side of the magnet. Okay, so for this one here, the north, which I'll just draw in green. So this is considered the north pole, and this will be considered the south pole. Okay, because this is considered an electromagnet. I hope that's clear. Okay, can you try pause the video now and try the next one, and then you play the video, the answers will magically appear. Okay, so you see that the current has swapped sides. If the current is swapped sides, the field pattern will also, the poles will flip, because right hand grip rule again, this top one is coming out of the page, so it's going to go this way, it's going to go anti-clockwise. This one is going into the page, right? This one here is going into the page, so it's going clockwise, and then you get like all of it bunched inside, and outside it's weaker. Okay, and then the poles for this one, right in red, this is going to be the north pole, and this is going to be the south pole, because you consider this as a magnet, and all the domains, or all the magnetic field lines are pointing towards the north. Okay, so I hope that was clear. So this is what it looks like for a single coil. So this is a single coil. What about how do we increase the magnetic field strength in the coil? Okay, how do you increase the magnetic field strength of the coil? Of course, just like the straight wire, a larger current would result in a stronger magnetic field. Okay, so a larger current flowing through the coil will result in a stronger magnetic field. So you can increase the current. What else can you do? Well, you can increase the number of turns of coils. Basically, imagine this. I now put another coil there, and then put another coil there, and then put another coil there. What do you see happens, right? This one has the coil of this field. If I stack another coil of it, there's suddenly the field of this coil. So I stack another one of it, there's the field of the second coil that is going to add to the same effect. Can you see they're all coiling within the coil? Of course, if you stack it on top, directly on top, I can't really do that with this picture, but you get what I mean, right? So you stack it directly on top, the effects of the magnetic field produced by the current gets added together. So can you see? The more I stack, the more magnetic field lines are added together, going into the loop around it, just like this. So the more number of coils you have, the more magnetic field strength you get, and really what you really get is a solenoid. Okay, that's why I talked about the flat coil first, because when you understand the flat coil, then we talk about the solenoid, which I will explain to you in the next video. Oops.